Hi, everybody, and welcome back to our helicopter lesson in 15 minutes or so. We're going to wrap up the helicopter components with the magnetic compass. It's one of the last instruments. Again, if you haven't seen any of the lessons before, go back there as well. It doesn't have to be in sequence, but it's important to see all of them to really make sense out of it. Remember, I'm taking a practical approach to it. I'm not, again, I'm a student for life, so what I say is mostly correct. Can it be expanded upon? I'm sure. The key to it is to make sure that you have dialogue with your CFII on each of the instruments. Sit in the aircraft, look at them, touch them, feel them, come up with different scenarios, come up with different ways of looking at it while flying itself. That's the better way of learning, rather than just looking at a bunch of slides or reading in the helicopter handbook. All good stuff, right? There's all accurate information there, but it's more important that we apply this in real life so it really can gets locked in. So always verify, but it's important for you to go out and look, see, touch, feel, and talk about it until it really sinks in and makes a whole lot of sense. You'll find out here that this stuff will make sense at some point in time. So listen, old sailors used to use compasses, right, along with the night sky to navigate while on the open ocean. So think about my ancestors went from Holland down to Indonesia, around the Cape, the Horn of Africa. Well, that is a long ways around the world, and they were able to find this over and over and over and establish these really trusted routes that they knew how much time it would take to travel point A to point B in order to be able to establish these well-known shipping routes for spices coming from Asia back into Europe. Well, crossing the Atlantic from Europe to New York City back in the day. All this was done through simple navigation using magnetic compass and looking outside. So today we are spoiled with all the instruments that we have, especially GPS, that is WASP enabled. That we have highly accurate information at the tip of our fingers, and we essentially speaking just have to fly the magenta line in order to get from point A to point B. But it is important, in case all of that goes away, that we remember where we are and what we are doing. Now, the cool thing about helicopter flying is that we often fly lower and slower. We don't fly long distance, right? 2 to 3 hours really max. And we more often than not we see the ground at all times. Now, more advanced systems will have instrument rated or single pilot instrument rated with autopilot on it. No such luxuries in the R22 or 44 at this point in time, right? So again, it's important that we know of all of the pieces of the components, how they work together, and what it is. So again, the old trusted instrument that we will see in our dashboard, often in the center pole, is going to be a compass. Right? We have two different types of compass. We have a whiskey compass, which is mounted on a beveled float on the slung that is sealed fluids, where the compass card is wrapped around opposite of the turn to show the heading. Most helicopters will have that one. The second option we have is a vertical compass, which you see on the right side of the picture over here. It is mounted vertically with just the card face showing, and it has a mechanical linkage that is doing exactly as the whiskey compass is doing, but you don't get to see it. Right? The information, of course, is still the same. And now in the more advanced aircraft, these are now electronic. Now, the differences between the old and the new is that, from time to time, we have to reset the mechanical ones, the HSIs, while the digital ones are automatically updated, and we no longer have to make adjustments along the flight itself. Again, two different things. But the magnetic compass in the center of the window is something that we have available at all times. And we have to understand how it collects information and where does it align to, and also become aware of some of the errors that are existing. Because again, if you have to navigate by that, you have to be aware of it, right? So the Earth contains a magnetic field that is connected from the North Pole to the South Pole by lines that are truly invisible. We refer to them as flux. The lines run parallel at the equator, right? But then they dip down by 90 degrees at the poles itself, which is an issue. When the magnet is free to rotate, it will always line up with the lines of flux, and at the north-seeking end will always line up with the magnetic north. And there's a difference between magnetic north and the true north, and we'll talk about that a little bit more. So there are inherent problems with because we can have compass errors. So we have a little acronym over here on the side. We can have variation, we can have deviation, magnetic dips, oscillation, northerly and acceleration errors that occur. So we're going to dive a little bit deeper into that because it is important, right? So at the true north, right, is actually as much as 1,300 miles away from the magnetic north, right? And that needs to be taken into account. So when we're looking at sectional charts, they orient it to the true north, not the magnetic north, right? Magnetic is the point where the lines of flux will come together, where they dip 90 degrees down, right? The direction of the north-seeking part of the compass needle will point due to the Earth's magnetic field itself. So it will actually literally dip. And there is some mechanical countermeasure put into play, but it still will have a tendency to dip. The closer you are flying to the North Pole, right, the true magnetic north, the bigger the issue that is, of course. Being in the Northeast, we're close enough that we have to take these things into account, and we need to learn about that. So the magnetic variation is the angular difference between the magnetic north and the true north at a specific point in place. So we need to know where we are so we can calculate what that means to us, right? So we are in the east, so we have to think about that. You know, how does that? Now you can go to the sectional chart. It will provide you with information on what you are supposed to do, adding or subtracting. So the magnetic variation is depicted by the isogenic lines on a VFR chart, similar to what you see right behind my picture there. The agonic line is the zero magnetic variation. So whatever you read is what it is. Anything to the west or anything to the east, we need to think about it that we have to add up, subtract. So again, remember this. East is least, west is best. So you subtract to the east and you add to the west itself. So that is something that we have to take into account if you truly fly by the compass itself. Now again, it is extremely unlikely that you will ever do that truly. But again, you're still required to learn that. Right? So the problem is that because you don't use it, you will forget about it. Right? You won't remember. This is something you will be tested on the FAA written exam. So again, lock these little things into play and look at them more often over the next week or two as you start flying. So it really helps you make sense out of it by actually making the connection. Now, interesting enough, in your aircraft, you should be able to find, there should be a magnetic compass correction card that is either on the visor or it's in a position or even on the T-bar. That you should be able to look at this so you understand what you need to do, adding or subtracting wise. Because, you know, again, it is the deviation part that if you follow it, you end up at the wrong spot. Now, again, yes, we're doing, pilotage. We're looking out of the window. We're following roads. We're following, key, visual indicators on the ground to go from point A to point B. Often we're really looking at an iPad or a GPS device. We're flying the magenta line and make sure that we maintain a positive track on that and make corrections for the wind. Again, this is something that just in case, you do need to have awareness about it. So the compass deviation errors due to magnetic field in the aircraft, such as metal parts and electronics. So that's called interference. One of the things that you will still hear is that when you go flying on a commercial aircraft, that you should not have your electronics on. That's probably one of the excuses that it could mess with the instrumentation. Is that true? I'm told there's no truth to it. But listen, we need to comply and do what they say, right? It can change based on what the equipment is on, and even what direction you are flying. Again, so there's variations in that. Mechanics make correction cards showing headings and what to steer to get to those headings itself. So again, it's the mechanical function of it. And mechanical have to change these when something new is installed. So again, when things change in the environment, when you get all new fancy equipment put in, which has larger electronic fields to it, it might negatively impact the compass, for which adjustments need to be made. So we talked a little bit about the magnetic dip itself, right? So any magnetic object, even the bar on the compass, will align itself to the magnetic field dipping towards the Earth. So at the equator, the flux lines are parallel, so there will be no dip. However, as you have higher latitudes or closer to the North or South Pole, it will want to tip forward. In order to be able to prevent it from happening, there's actually a countermeasure on the backside that holds it more level. Now, the closer to the North Pole, where likely any one of us will be flying, is not that great, it becomes more significant. But that also has an effect that when things are rotating, like you're making turns, we have to take that into account. And that's really more important that we learn about, right? So the oscillations, right, is the error in the compass due to turbulence and airspeed changes moving and shaking the compass card. Right, it might read north 1 second and northeast the next few seconds, just because of turbulence. Right, the good rule of thumb is to turn to the average of those shifts, meaning don't follow every wide shift you see. Right, it's like chasing your tail, and you'll never catch up. Slow down or land if turbulence makes it impossible to navigate correctly. And what is the likelihood that you will be using a compass card to navigate from point A to point B? Not good. Again, as a backup instrument, and it's rock solid advice that if you cannot see where you're going, if it is too turbulent, the luxury of the helicopter is land, wait it out, and then fly again after that. So the more important ones that we need to remember, and again, these will be on your FAA test, so you have to make sure that you understand this, are two acronyms. The first one is ANDS, or accelerate north, decelerate south. So this happens only when on an east or west heading. Right? The other one is north to south, east and west heading. The weight is located on the south side of the compass, right? We just talked about that, the countermeasure from it dipping into the north itself. The inertia causes initial lead or lag on the compass card when speeding up or slowing down. So think of it being in a car and hitting the gas, and you're being pushed back or slamming the brake and going forward. The same thing happens with the compass, right? So also during these turns, the compass is free to rotate and will try to align with the lines of the flux. So we actually get indicators that are not exactly accurate, but we have to remember that as we fly, so we could take that into account, especially when we're accelerating, decelerating, and making turns, or we want to end up at a very specific, heading. Right? We need to turn out sooner or slightly later, depending on where we're going. The other one is UNOS, is undershoot north and overshoot south, right? And that is if you're on the east or west heading, right? And you're going to the north or to the south. So when turning to the north, the magnet will want to chase the magnetic north and turn faster, further than the helicopter. So we want to undershoot the north turns. So if you want to end up at 0, you really have to think about it maybe at 010. And the flip side is true. If you want to go to 180, you might have to overshoot it to 190 before. So when you roll out, you end up on the right heading itself. Now, there's some calculations that we can make in that, and we'll cover that in a second. The other magnetic compass errors is that the needle lags when turning from the north. As we turn from north, we initiate an angle of bank. The bank and the north-seeking end of the magnet wants to continue to dip towards the Earth, as we discussed. And you have that countermeasure on the back side, right? On the flip side, the needle leads when we're turning to the from the south. As we turn from south, we initiate an angle of bank. The north-seeking end of the magnet wants to continue to dip towards the Earth. So it shows an indication ahead of the direction of our turn, and that's leading. So one is lagging, the other one is leading. The error will correct itself once the turn has been completed. And again, I would say next time you go flying, ask the CFI to demonstrate this to you. So you can look at the compass and see what actually happens. Once you see it in real in life scenario, it will make a whole lot more sense than just listening to me or reading off a slide, right? And it is not the best ways of learning. So this is the final slide, and this is something that obviously becomes more important as we go from private to to IFR to commercial rating. You have to become more precise. So knowing when to roll out to end up on the heading that you desire to be on is something that you will be tested on. So it becomes more and more important. And yes, we have a magnetic compass and we have errors, but this is something you have to calculate with a heading indicator as well, right? So that doesn't change in that sense. So we have a couple of things that we can do from fixing particular purposes, is that we can make these minor calculations that we need to anticipate the time it will take to roll out of the turn. And to do that is to equal to the half of the bank angle used. So if your bank angle is 20, right, we want to roll out 10 degrees prior to the desired heading itself. So if you want to end up at 0, you're coming from the east, you want to roll out at 0, 1, 0. So once you roll out, you're going to be at the heading that you have intention on. Of course, you also have to correct for the magnetic correction that we just talked about. So again, the best way to demonstrate is by asking your CFI to do it for you while you are just looking at the instruments, right? Focusing on one thing. Look at the heading indicator, look at the compass, and see what has taken place when you make these changes. And I promise you, once you see it and experience it, it makes a whole lot of more sense than just reading or listening about it. I hope this was helpful. And again, helicopter components are critical importance, right? Seek out your CFI, seek out your mechanic, ask good questions, and keep coming back to this over and over and over until it really sinks in. And again, as my father always said, see one, do one, teach one. Part of the reason why I'm putting this out, this is about teaching, right? It is about me trying to get to a level of competency, proficiency, so I can talk about this with not just skin deep, but really with a certain level of expertise. And that I'm certainly still building, right? That comes over time. But again, short spurts, 15 minutes a day. Thank you for being here, and we're going to the next topic in the next session. Have a great day.